So now similarly the final error analysis that we are going to do is for a unit parabolic reference input. Okay, so what is a unit parabolic reference input? This means that u of t is t squared by 2. Okay, this implies that sorry, not u of t, r of t, right? So r of s is going to be 1 divided by s cube. Okay, so that's what will happen. Okay, so this implies that ESS, which is 1 limit s tending to 0, s times r of s divided by 1 plus g of s h of s, that is going to be limit s tending to 0 1 divided by s squared 1 plus g of s h of s, which is going to be equal to limit s tending to 0 1 divided by s squared g of s h of s. Okay, so that's what we have. Okay, same process, nothing different. I hope I am doing things correctly. Okay, please stop me if I am making an error somewhere, right? So similarly, just like what we did above, we define what is called as a static acceleration error constant. Which is defined as KEE is going to be limit s tending to 0 s squared g of s h of s. Okay, so that's the definition. So this immediately implies that the steady state error is 1 divided by KAE. Okay, so that's what we'll have. Okay, so similarly, if we construct a table like before, for this case, we can immediately observe that for type 1 and 0, KE will be 0 because it's s squared. You can immediately it's straightforward to figure out that the static acceleration error constant will be 0, right? Okay, so steady state error will be infinity. So in a certain sense, if you want to see what is a parabolic reference input, now how will this look like? So if you plot r of t versus t, so our t squared by 2 is going to increase something like this, right? Correct? So that's a parabolic input, right? So if you want to, of course, once again it's an unbounded input. Please remember that, right? But if you want to track that input, right? So I need like at least type 2 or higher, right? So that's what will happen. So KAE will be capital K for type 2. So the steady state error will be 1 by K. And only when type 3 or more, for type 3 or more, the steady state error will be 0. You can really check it. Okay, so this is what will happen if you want to track a unit parabolic input. Okay, fine. So essentially we divided by 2 so that like it comes like 1 by s cube.
But then unit, doesn't that mean the code? What is unit parabolic?
So essentially what we are doing is that we are, instead of just calling it t squared, we are doing it t squared by 2 so that like it comes like factor like 1 by s cube. Okay,
but does that mean it's not a unit parabolic?
That's a definition, no? That's how it's defined.
It's defined that
Yeah,
way.
so it's called that way. Yeah, so, yeah. if you have a unit parabolic input, the r of t function, time domain function is t square beta. Okay, yeah. So of course, since we are dealing with linear systems, like you can still consider t squared, right? So you will just have a factor 2. That's it. Okay, so it doesn't matter. Okay, so that's the steady state error to a unit parabolic input. But see, my aim here was twofold. The first thing for us, because by and large we would be interested in tracking, like step inputs, right? So I wanted to show that we need at least one integral term in the open loop transfer function. That was point 1. 1 by s can come either from the plant or the controller, right? Please remember that. So you the statement that integral controller will remove steady state error is correct, but then you don't need an integral controller always to remove zero steady state error to a unit step input. That is, that you need an integral controller to remove to remove non-zero steady state error. I am sorry, to only if we do not have a 1 by s term in the plant transfer function to begin with, right? So at the end of the day, we need a type 1 system, all right? So if you want to have zero steady state error while tracking a step input, okay? So that's one thing. And I also wanted to introduce these terms, right? Definitions of these terms: static position error constant, velocity error constant, and acceleration error constant. Okay, so that was the aim, and the structure of the open loop transfer function, which is also quite useful for us, how we wrote it down, right? So k times in this way. Okay, so this is a structure which we will utilize later also, right? So you give me any open loop transfer function, I can rewrite it in this manner, right? So that's something which we already looked at. Okay. So the next topic which we are going to start today is that of root locus. Yes, please.
Why can't we just use type 2 systems for even unit step?
Okay. Type 2 systems. Okay. So that we are going to answer when we will get a clearer picture when we do root locus. Okay. So his question was, why can we not use a type 2 system to begin with? The problem is that the moment you have a type 2 system, you have a 1 by s squared term, right? You have two open loop poles at the origin. Okay, even we will shortly see that even stabilizing with one open loop pole at the origin is going to be challenging. Two open loop poles, it's going to be even more difficult. So the moment you keep on increasing the number of open loop poles at the origin, stability, closed loop stability becomes a challenge, right? So in this analysis, we are assuming that closed loop system is stable, but practically stabilizing it is going to be difficult. Okay. Okay, let's do root locus. Okay, so what do we mean by root locus, right? So as the term indicates, it is a locus of some root, right? See, all of us know what locus means, right? So it's just a trace of something, right? As a parameter is varied, right? So that's what we call as a locus, right? So what is root locus? This is the locus of the closed loop pole poles as a system parameter is varied. Okay, see, for example, if I vary the open loop gain K, capital K, okay, which came in the previous slide, right? How does the closed loop poles vary? Okay, so once again we are going to consider the same block diagram which we looked at. See, this is the reason I spent quite a bit of time in constructing these block diagrams, right, and explaining what each block represented. Okay, so we take this block diagram. Okay, so immediately the closed loop transfer function which is nothing but y of s divided by r of s. We already know that it's going to be equal to g of s divided by 1 plus g of s h of s. Okay, so immediately we know that the closed loop characteristic equation is given by 1 plus g of s h of s is equal to 0. Okay, that is the closed loop characteristic equation, right. So, because y 1 plus g of s h of s is what is called as a closed loop characteristic polynomial, 1 plus g of s h of s equals 0 is what is called as a closed loop characteristic equation. The roots of this equation are the closed loop poles. Okay, so please note that the roots of this equation are the closed loop poles. Okay, so that's something which we already know, right. So now let us look at this closed loop characteristic equation in more detail, right. So I can, if I write 1 plus g of s h of s equals 0, this implies that I can rewrite this equation as g of s h of s equals minus 1, right, is it not, right. So I am just taking it to the other side. So any value of s which satisfies g of s h of s equals minus 1 is a closed loop pole. Do you agree? That is just an algebraic manipulation, right. And why is this significant? What is g of s h of s? It is the open loop transfer function, right. So that is the definition of g of s h of s, is it not? G of s h of s is what is called as the open loop transfer function. So what can we infer from this? That any value of s that makes the value of the open loop transfer function to be minus 1 is a closed loop pole. Do you agree? Correct. So that is another way of interpreting when what it says a value of s would qualify as a closed loop pole, and we are going to use this repeatedly to our advantage, as we will see shortly. Please note that s is a complex variable, right, and g of s h of s is a complex valued function. In general, g of s h of s can be a complex valued can take a complex value, right, because that is a complex valued function of s, right. So the moment we have this equation I can rewrite in two terms, okay, because any complex variable will have a magnitude and a phase. So if I have g of s h of s to be 1 minus 1, that means that at that value of s the magnitude of g of s h of s should be equal to 1, right, and the phase of g of s h of s should be equal to 180 degrees. In general we write it as plus or minus 180 degrees times 2k plus 1, okay, so that is the general way of writing it. So essentially what we are saying is that it is an odd multiple of 180, right. So that is the way of writing it. So this condition is what is called as the magnitude condition. Okay, this condition is what is called as the angle condition or the phase condition, right. So of course some people will call it as a phase condition, right. So you see that from the closed loop characteristic equation we have got two conditions, right, and any value of s which satisfies these two conditions is a closed loop pole. I am sure we are still in agreement, right, through this process. Okay, so any value of s which satisfies the magnitude of g of s h of s equals 1, and the phase of g of s h of s is as an odd multiple of 180 degree is a closed loop pole, right. Okay. Now the question is that how are we going to use it to our advantage? That is what we are going to learn, right, when we do root locus. So let us consider that the open loop transfer function takes the form okay, g of s h of s is equal to some k times, of course please note that this k is different from the one that I used before, okay. So k times s plus z1, s plus z2 all the way till s plus zm divided by s plus p1, s plus p2 all the way till s plus pn. Okay, so by and large you can rewrite in this form. Please remember that in the previous discussion on steady state error, we used what to say, a k such that the constant terms in the numerator and the denominator polynomial were 1. Here it won't be. Please note that k was known as the open loop gain. This k is something else, it's a parameter, okay, but unfortunately the same symbol is used. So please we should not get confused between the same symbol. I could have called it something else, but in most textbooks you will see that this will be the structure will be followed, okay. So I don't want us to essentially follow a different notation, okay, that's my only motivation, okay. So of course you see that I have factorized the denominator and the numerator polynomials. So you can see that the numerator polynomial is of order m, denominator polynomial is of order n, right. So that structure is something which we are still keeping, right. So immediately we can see that there are m open loop zeros, right. What are the m open loop zeros? Minus z1, minus z2 all the way till minus zm, right. So there are m open loop zeros, do you agree? Okay, and there are n open loop poles. So I am sure all of us remember what are meant by open loop zeros and open loop poles, right. Open loop zeros are the open loop transfer function, open loop poles are the poles of the open loop transfer function, okay. So what are the n open loop poles? They are essentially minus p1, minus p2 all the way till minus pn, okay. So those are the n open loop poles, okay. Now what is the question we are going to ask ourselves, right. So the question we are going to ask ourselves is the following, okay. So before that, like this essentially implies that you can immediately see that there would be n closed loop poles. Why? Because the moment you calculate 1 plus g of s h of s equals 0 and take LCM, you will get an nth order polynomial. Do you agree? See, because if the order of the open loop transfer function is n, the order of the closed loop transfer function will also be n, okay. If you evaluate 1 plus g of s h of s, you would see that will be an nth order polynomial, right. So you will be solving for n rules. So you will have n closed loop poles. I hope that's clear to everyone, right. So the question that we are going to ask ourselves is that how would the n closed loop poles vary with respect to the open loop poles and the open loop zeros as the parameter k is varied. Okay, of course k we consider to be a real parameter, right. So as a parameter value of the parameter k is varied, okay. So yes.
The poles will be same as open loop poles. Why will the poles?
Okay. Why would the poles be different, right? So because to answer that question, let's go here, right. So what will be 1 plus g of s h of s here? It will be 1 plus this, right. So I'll have s plus p1. Denominator remains the same, okay, but we are evaluating for the numerator, right. So okay, so the closed loop characteristic equation will be this. Of course, you will have divided by s plus p1 times s plus pn, that you anyway like take it to the other side, it will become 0. So essentially if you solve this, you are solving this. So obviously you see that the values of s are different, right? They depend on the value of k. Okay, that's a good point. So I am going to leave you, you are preemptively given part of the answer to questions I am going to leave you with. Okay, so essentially, yeah, this is the question we are going to ask ourselves, and the answer is the root locus provides a graphical representation. Okay, we will see that the root locus provides us with the corresponding graphical visualization. Graphical visualization. Okay, so what we are going to consider is the following. Okay, so we would first consider the case when the parameter k is non-negative. Okay, then we will see what happens for the other case also. Okay, we will go one case at a time, right? So that means that k is greater than or equal to 0. Of course, strictly greater than 0, because equal to 0 doesn't make sense. Okay, so essentially k should be a positive parameter, right? So, but we will take the limit also, right? So essentially what we need to say is that what happens when k goes from 0 to infinity. That's what we are going to look at first. Okay, so I am going to leave you with a couple of questions, right? So what happens to the closed loop poles as k tends to 0 and k tends to infinity? Okay, the answer is very evident from the thing that we wrote down to your question, right? So what we wrote down here, immediately you can figure out what happens as k tends to 0 and k tends to infinity. What do you think will happen as k tends to 0? The closed loop poles will tend to the open loop poles. And what happens as k tends to infinity? Closed loop poles will tend to m open loop zeros. What will happen to the other n minus m closed loop poles? We will see what happens. Okay, so that's something which we are going to you think through, and then like we'll answer it on in the next class. Okay, the second question which I am going to leave you with is, anyway we will revisit the answers. Okay, so please think about it. Okay, we are going to revisit these questions and then like discuss all the answers. And how do we check? Okay, I think let me put it this way. Okay, how do we check how when a polynomial has multiple roots, right? Essentially repeating roots, you know, like what characteristics would the polynomial have, right? So let me put it this way. How do we check if a root of a polynomial has a multiplicity greater than 1? So that means that we are having repeating roots. Okay, so how do I check if I give a polynomial, I tell you that something is a root, right? How do you check whether, what characteristic will you get, right, if you have a repeating root? Obviously if you give any polynomial, you give me any root, at that root the value of the polynomial should be 0, right? That's the definition of a root of a polynomial. But that's true for any root, right? So but then if I know that some root is repeating, you know, like how do I check that, right? So that's something which you think about and come, okay, because these answers are going to become pretty important when we learn the root locus. Fine, so I'll stop here and then like we will meet on Monday, right? So yeah.